Oh, I think they're very, very different. You know, they address deep scientific questions, but in such incredibly different ways that it's very hard to say that there's a similarity. What I can say is that people, so for example, in my own working life, you know, first I did particle physics in the quantum field theory way, and then I did string theory, and then I got interested in biology and I started thinking about biological problems. It's not that biological problems look at all like problems in string theory when you sort of hold them together in your left hand and right hand and look at them. It's just that, I don't know, the way you think about setting up problems, the way you think about analyzing them, the way you think about bringing mathematics to bear, it's similar in spirit, but in so many details, it's really different. So it's exercising a different part of your brain. It's interesting, actually. So I've followed or been involved with quite a few young people who have, as graduate students or just beginning postdocs, were trained in string theory, and then they decided, well, for one reason or another, that they wanted to try working in biology. And I've been really impressed by how quickly these people, who are clearly highly, you know, they're very good mathematicians, they're very good at creating mathematical tools to deal with new problems, how quickly they were able to take that intellectual skill and bring it over to what is a really different domain of science. In one of the classic fields of science, there's been such rapid progress over, you know, just one lifetime, really, that, you know, you can see how you've gotten to a point where you've answered so many of the questions that were posed in the past, or that weren't even posed because you didn't know how to pose them, right? This pace of progress is something that is not obviously sustainable for forever, right? So there's a question of, are there limits to what you can in fact learn about the universe in any areas? Well, the place where there's absolutely no limit to what you would like to learn, it seems to me, is in biology. That is to say, you know, what is it that characterizes living matter as opposed to inanimate matter? How does it, what is it that makes it different? How does it arise, and how does it actually work? My point is that there's just a whole raft of questions that we don't obviously have the ability to answer now, and it is not obvious that we will be able to progress as rapidly in that domain as we did in the domain of cosmology or particle physics, because the problems are genuinely hard, the systems are genuinely complex, and all the rest of that. But it clearly is an open field for innovation that probably will require that we pursue them in ways that are significantly different from the way they were pursued in the past. I mean, I think biology, the way people practice biology, is changing and has to change. And so there's an interesting intersection of changes in attitude and situation of the science in both physics and biology.